So this is a fun one. Can you try and identify the relationship between Fourier series on one hand and Laurent series on the other hand? So pause the video and try and have that fun. We know that Fourier series, they're only defined for periodic functions. So let's consider a periodic function. Let's say we call our function f of chi here, and the horizontal axis is the chi axis. If we have a periodic function with period L, then we know that this will correspond to an angular frequency omega being equal to 2 pi over L. And let's write down the Fourier series f of chi. So we know that we can write this as a constant DC term. Let's call that one A0. And then a sum of sines and cosines. So let's go ahead and write a summation of n going from 1 to infinity of an cosine n omega chi. And then also another sum involving the sine. So sum of n from 1 to infinity. And let's call the coefficients here bn, sine n omega chi. Now, for our purposes, it will turn out to be much more interesting to split both the sine and the cosine as a sum of positive and negative complex exponentials. And if we do that, if we can group terms either with positive or with negative complex exponentials, we can also write this whole thing as a summation of n going from minus infinity to plus infinity in this case, coefficients which we will call Cn, and then exponential Jn omega chi. Now here we are already very close to our Laurent series, because what we can do here is make a certain substitution where we say a complex number z, we're going to write that as exponential J omega chi, right? And if we make that substitution, it becomes immediately obvious that if we raise z to the power of n, that we get exponential Jn omega chi, which is exactly the type of stuff that we find here in the series expansion. So we can massage this series expansion a little bit to give us something which really looks a lot like a Laurent series. So a sum n from minus infinity to plus infinity, Cn, and then z to the power of n. The only thing which is missing at the moment is that this is a function which takes a real valued argument chi, whereas for our Laurent series, we would really like that to be a complex valued function. But what we can do is play a trick called holomorphic or analytical extension, where we just take this real valued function here and extend it all over the complex domain. So then, by generalizing this small f, if you want, we can end up with a capital F of a complex function, of a complex argument z, which is given by this Laurent series. So obviously, if you then take that Laurent series, which we've defined here for that extended function f of z, and if you evaluate that Laurent series on the unit circle, so if you evaluate f of exponential J omega chi, then you get indeed back the function we started from, f of chi, which we've written down as a Fourier series. So this is the relationship between Laurent series and the Fourier series. Basically, if you have a complex valued function, you extract a periodic function from that by looking at the unit circle, and then by running around on that unit circle, for example, starting here, chi equal to 0, and then ending up at chi equal to L, you see that basically you've created a periodic function, because this will keep on repeating itself with period L. And that function we can calculate the Fourier series by taking the Laurent series and evaluating it on the unit circle.